Hi, this is the first video of the introduction of analog CMOS design course. First, I will start with the fabrication of the CMOS transistor. Then I will move to the physics of the CMOS transistor, first with 2 terminals, then I will move to 3 terminals, and then finally 4 terminals. Let's start with the CMOS transistor. Well, in the integrated circuit design, CMOS transistors are the main component, and we have two types of CMOS transistors, NMOS and PMOS. In the NMOS transistors, the current is generated by electrons, and while in the PMOS, the current is generated by holes. In both transistors, we have 4 terminals: drain, source, gate, and substrate. The current in the NMOS flows from drain to source when we inject a voltage between the gate and the source. Notice that here the gate voltage should be greater than the source in order to generate this current. If the substrate is connected to the ground, then we can use a 3-terminal figure as you see below. And in the case of the PMOS, in order to generate current from the source to the drain terminals, we need to inject a voltage from the source to the gate. Notice here that the source voltage should be greater than the gate. Again here, if the bulk is connected to VDD, then we can use a 3-terminal figure as you see below. For the fabrication process, we start with a silicon die, and we dope this silicon with atoms so that we can generate a p-type semiconductor. After growing this p-type semiconductor, we will grow another type of semiconductor, in this case n-type, for the source, for the drain, and also we will create a connector for the substrate by growing also up the same type of the semiconductor P, but this will be highly doped. Notice that the substrate is low dope, and the source and the drain have high dope concentration. Between the source and the drain, we will insert an oxide here, which will work as a dielectric, and above the dioxide we will grow polysilicon, which is a conductor material, so that we can generate a capacitor between them. This capacitor will try to attract electrons close to the surface of the oxide. For the PMOS, the process is similar, just that after growing the substrate p-type, we will grow also a well with n-type. This will separate the NMOS from the PMOS, and once that we have the n-type well, we will grow semiconductors p-type with high concentration for the source and the drain. Again, we will have an oxide and polysilicon to connect the gate terminal. For the well N, the connector will be created by generating a highly doped semiconductor n-type for the bulk. And we have some insulators between the transistors, which is called FOX. We had the front view here, but we can also obtain the top view. As you can see here, the gate contains a length L, and the width of this gate is W. For the PMOS, we have the same figure, just that the terminals are inside a well. Now let's move to the physics of the semiconductor. First, we will analyze the gate bulk terminals, and as you see in the graphic, the bulk and the gate will be between those terminals. We will insert a voltage VGB. Initially, when this voltage VGB is equal to 0, our transistors will be neutral, but there will not be charge. Remember that in the p-type semiconductor we have positive charge here, but then when we increase the VGB voltage, the charge on the gate will repel those positive charge, they will move down, and what we will get them is a negative charge, no? But this is fixed charge, no? Ions will be in the surface, close to the surface, and then when we increase more the voltage VGB, finally we will obtain free charge or electrons. This here, no? These electrons will generate a charge Qi, and the ions here will generate a charge Qb. The total charge in the substrate or in the bulk will be Qc, which is, as you see here, Q sub I plus Q sub B. Then we have one first equation here about that relates the charge. In the oxide we have a relationship of the capacitance equal to charge over B, over B, and we have also the surface potential. Those equations plus Poisson equation can give us the solution for the relationship between the gate bulk potential and the phi sub s potential, and the relationship between the voltage GB and each of these charge. When we solve those equations, we have expressions for each parameter very long. So what we will see here is only the plot of this solution. First, we will start with the weakened version. In the weakened version, we had only ions here and very few charges, or very few electrons, free charge. And when we increase the VGB, the relationship of this surface potential will be almost linear, as you observe the first part. But then when we increase further the voltage VGB, we will not continue to increase the surface potential linearly. So the slope will be reduced, and this is because now electrons have been generated moderately, and finally when we reach a threshold voltage around close to here, a small increase in VGB will produce a large amount of electrons of free charge. Okay, so the voltage or the surface potential after VH0 will tend to be almost flat. Similarly, for the charge, here we see that in weakened version the charge is basically dominated by Q sub B, which is the charge of the ions. But then when we move to a strong inversion, charge starts to be generated due to the electrons, the free electrons, and it will represent the most of the charge when the voltage VGB is greater. Okay, well, in strong inversion we can use some simplifications. For example, we can say that the potential after the threshold will be almost constant, and below the threshold we will not have potential, and also that the charge will be, the total charge will be approximated to Qi. Well, now let's add another terminal, the source terminal, and let's inject a voltage between the source and the bulk, VSB. The higher voltage will be into the n-type semiconductor, and the negative into the bulk. So as you see here, we have reverse bias voltage. The plus goes to the N and the minus to the p-type. Since the p-type has a low doping concentration, the reverse bias will be greater, while in the n-type semiconductor, since we have a higher concentration here, the depletion region will be almost negligible. Not here we can have n charge, plus charge, positive charge, but it's almost negligible. So the generation of this depletion region close to the source, we will increase the charge, and in order to keep the same charge provided by BGB in the gate of the transistors, we need to reduce the free electrons, because the total current, the total charge is the charge provided by the electrons and the ions. If we increase the ions, then we have to reduce the electrons to balance the current, to balance the charge. Well, so far we have used the bulk as a reference, but in order to simplify some mathematical expressions, we can use the source as a reference. And if we do that, then the voltages will have to be modified. We will have VGS voltage between the gate and sources, and the VSB voltage between the source and the bulk. This BGP voltage here will be equivalent to VGS plus VSB. As you see in the first graphic, the charge due to the free electrons is provided by the capacitance on the oxide times BGB minus the threshold respect to the bulk. But here, similar, we will have that the charge is equal to the capacitance in the oxide times BGS minus PTH. Now we are using BGS, but this PTH will be equal to the threshold on the bulk minus the voltage VSB. So as we see, if we replace those expressions here, the charge in these two equations are the same. Now let's add the other terminal. We will add the drain, and this case is similar to the source. We will inject a voltage between the bulk and the drain, and this a reverse voltage, and this will create a depletion region close to the drain. Here we have ions, and also here we have ions. But if we consider that the voltage on the drain is greater than the voltage on the source, then the depletion region close to the drain will be greater than the depletion region on the source. So if we have greater depletion region here, we will have less electrons close to the drain and greater electrons close to the source. As you see here, we have created a gradient of electrons, and if we have a gradient, then we can generate diffusion current. Well, thank you very much for your attention. The reference that I have used is the following.